Good morning. My task is in the next few minutes to give you a brief introduction to NIRISS because we haven't talked about the instruments yet. So, brief introduction. I want to speak with you about imaging with NIRISS, and I want to talk with you about our high contrast imaging mode, aperture masking interferometry, which doesn't actually fit neatly in with the coronography session later this afternoon. So, that's a tall order. Let's get going. A bit about NIRISS. So, here's a picture of NIRISS when it arrived at the Goddard Space Flight Center in the land of the bunny suit people. Is it on? Is it on? Is it on? Yeah, good. Okay. And so you see that it's all metal, and it's just about the size you can get your arms around. You can give it a hug. It was developed by the Canadian Space Agency and provided by the Canadian Space Agency. The principal investigator is Professor René Doyon of the Université de Montréal, and the prime contractor was Honeywell, formerly known as ComDev. Technical research, technical development was done by NRC, National Research Council of Canada. Here's another picture of it, and this is just to remind me to tell you that you almost always hear NIRISS and FGS in the same breath, and that's because they're joined at the optical bench. They are two instruments on the same platform. So here's the optical bench. This is FGS. This is NIRISS down here with the kinematic mounts to the ISOM structure. So it's packaged with the fine guider sensor and has essentially nothing else to do with it. They share a teeny bit of flight software. Otherwise, no connection whatsoever. NIRISS is the science instrument, so that's what we're talking about right now. NIRISS is the simplest of JWST instruments. So here it's an efficient, all-reflective design. Here is the optical path of it, and you see what I mean. There's a pick-off mirror. There's a pick-off mirror. Where does it go? Can't see mine. There we are. Pick-off mirror, a collimator, bounce, bounce, bounce. A pupil is formed here with a pupil wheel and a filter wheel. Then a camera, bounce, 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 and one detector. That's pretty simple. We talked a little bit about detectors yesterday. This is one of these Hawaii 2RG detectors with a 5.2 micron, the same as the long wavelength channel of NIRCam, the same as the NIRSpec detectors. And it has 2048 by 2048 pixels, 2040 of which are active. They're on 18 micron pitch. This is our best current estimate of the dark rate from cryovac testing, best estimate of the noise, gain, field of view, and plate scale with, as Massimo said, very small amount of distortion. So it's a simple instrument. And you say, well, actually, what can this thing do? It's so simple. Well, obviously, all the functionality is in the pupil wheel and the filter wheel. And here is the layout of those. You see that there are various filters in the pupil wheel. So the darker blue ones are wider, the W's that Massimo was just talking about. The lighter shades are the medium band ones. There's a clear thing, which means you can stick your finger through it. There's nothing in there except for this optical alignment element for ground test. Whoa, here we go. One more. There's a grism and a mask, which we'll talk about. In the filter wheel, there's more grisms and more filters. So what can that do? Well, that can enable 4 modes. The imaging mode, which we call imaging. The aperture masking interferometry mode, which we'll talk about, which we call AMI. And wide field slitless spectroscopy, WFSS. And single object slitless spectroscopy, SOS, which Chris Willett will talk about this afternoon, later today. So that's what's enabled by the things in the pupil and filter wheel. So I'm supposed to talk about imaging. So we have 2 channels of imaging. Blue, which are the blue filters in the, surrounded by green circles cunningly, in the pupil wheel, and crossed with the clear aperture here in the filter wheel. All these are NIRCam flight spare filters, except for the F158M. There's a reason for that, but you have to buy me a drink. Similarly, there's a red arm where we can use these narrowband filters or these wideband filters with this clear thing. The obstruction in here takes away about 16% of the transmission. So that's unfortunate, but there you are. Here's what the filter profiles look like, marching through in wavelength, and you can see the W's and the M's reflected here. These are the same color codings as in the previous slide. And I've also indicated our current best estimates of the sensitivity for the various filters over here. You don't have to remember these. We'll put them up on the web. But in nanojanskis, numbers like this, very similar to the NIRCam numbers. The Vega magnitudes sort of at the blue ones are 27, 28, and at the red ones 24, 25 in that area. This metric is signal to noise of 10 in 10 kiloseconds, so 2.8 hours. Right, so imaging, some caveats and some counseling. So NIRISS needs imaging because we need it to enable some of our other modes. It's an essential part of data collection with the wide field slit spectroscopy mode, and it's an optional component of the AMI mode, which we'll talk about in a minute. This imaging with NIRISS provides a powerful parallel capability when, because the filters are matched with NIRCam. And have comparable sensitivity. So it increases the aerial coverage if you're operating in parallel with NIRCam. If you're not operating with NIRCam, or maybe even if you are, under some circumstances, if you're really data limited, you might want to use NIRISS instead just because it has a lower data rate. We have 1 detector, not 10. So that actually my colleagues and I haven't actually thought of a use case for that yet, but I mention it nonetheless. However, let's get real. NIRCam is the workhorse imager for JWST. Why? It has twice the field of view of NIRCam. It observes in the blue and the red wavelength channel simultaneously, so there's a multiplex advantage of 4 right there, and it has much better sampling of the PSF at shorter wavelengths. So our recommendation, even though we love our instrument very dearly, is that you use NIRCam for almost all of your, well, yes, for your imaging, near-infrared imaging needs. That said, there is a NIRISS imaging template in APT, and it only really supports parallel operations. As I've said, that is the niche for where NIRISS imaging will shine. Because it's in parallel, you want to make wider aerial coverage on the sky. So this template doesn't support subarrays. That's not how you get wider coverage. And it doesn't have any information about the dither patterns that Massimo was just talking about, or mosaicing strategies, because you're the parallel instrument. You're just following the prime instrument doing whatever it's doing around the sky. So that is how we view imaging as imaging with NIRISS. So shift gears now. Let's talk about our aperture masking interferometry mode, AMI. This is the first space-based implementation of aperture masking, and we're actually quite enthusiastic about it. So in terms of the components, you use this aperture mask here, the non-redundant mask, NRM. We'll talk about that in a minute. With any of these filters here, these narrowband filters, or with slightly reduced quality, this wideband filter here, these are allowed combinations. These filters are cunningly chosen to sample key parts of the spectral energy distribution of brown dwarfs and exoplanet atmospheres. So here's the non-redundant mask. This is the cheapest optical element in any wheel or grating assembly on JWST. This thing costs $700 to make. It costs much more to design, but our time is free. So you see on this mask here, it costs a little bit more than $700 because it had to be coated black after this picture was taken. So you see, this is in the pupil plane. So you see the pupil of JWST. You'll see all the segments lined up. There's the support structures. And it's got holes punched in at 7 places. So it's a mask that lets through only about 15% of the light. Crazy. Undersized apertures. There are 7 times 6 divided by 2 equals 21 independent baselines. Baselines are pairs of distances between pairs of apertures, and each of those are very cunningly designed to be unique, so that the vector separation between each of them is unique, which samples the PSF in a way that is absolutely unique. So that you can disentangle all the nastiness that happens to normal PSFs. So it's non-redundant. It's a mask because it eliminates a lot of light, and it's non-redundant because all the baselines are different. Here's what the what the here's a simulation of what it looks like through the F430M mask, and you see that it looks pretty funky. This is 80 pixels by 80 pixels. This is oversampled data. I mean, this is a simulation, so it looks great. We call this the NRM PSF, or the interferogram. We use those terms interchangeably and in more informal settings. My colleagues at the University of Montreal, who know a lot about snow, call it the flocon de neige or the snowflake. Here's AMI in simulated action. This is what AMI is good for. It's good for looking for faint things close to bright things. So in the upper panel here, there is a direct image. These are simulations again of an 8th magnitude star, and over here is an 8th magnitude star with a companion that's 207 milliarc seconds away that is 1 magnitude fainter. And when you get your data from JWST, you'll be able to see things like this, that there's a companion there because there'll be an arrow pointing to it. So you can see in the snowflake's different, and that's the whole point. The key point, though, really, is why this is a cool mode is that as the separation decreases, it increases here. So things that are far apart will be easily detected by direct imaging. Things that are close together, AMI may have a shot at getting at. So that sounds like magic. Here is what's really going on. The left-hand side shows the regular pupil with of JWST with a high dynamic range simulation of the PSF. There it is. This is the width is 5 lambda over d, and you know it's a funky, airy disk there. The PSF core right here, this is now 0.75 lambda over d, whereas the full width is 2.44 lambda over d, airy disk. And if you put the non-redundant mask in, you get something like this, the snowflake, and the core is sharper. So that's all that we're doing. We're making the core sharper so that we have better spatial resolution for bright stuff because you're throwing away most of the light. Right. So the niche for AMI is looking for things that are close to bright things that are very close in, 70 milliarc seconds, that's the size of a pixel, to 400 milliarc seconds at intermediate contrast. Here's one example. There's an old plot. There might be an updated one of the near-cam wedge coronagraph, which the inner working angle is 4 lambda over d, so it can't see anything inside this green dashed line, which is exactly where AMI is operating. On the other hand, near-cam can do higher contrast. So these are very complementary capabilities. Higher contrast further out, lower contrast, but nice and close in. Very quick operational flow. Operational flow of an AMI visit. All the action happens in an 80 by 80 subarray up here, 5.2 by 5.2 arc seconds. And well, there it is right there. Let me walk you through it, just taking out some highlights here. First, there's a target acquisition. We have to know the position of the source very accurately. That happens next to the science subarray, not in the science subarray. So there's the snowflake. You can do a target acquisition on the snowflake or on a normal PSF, whatever you want. And okay, there we go. If that's a little faster than usual, but there we are. After that, we have to configure the instrument. Probably you're in the correct filter already, but you might want to change the filter. You obtain an image at that first dither position. Then typically you will dither 4 times. You can change that a little bit, but 4 dithers, and at each dither step you repeat the exposure. So something like that. Now, you also have the option at each dither step of micro-dithering by a sub-pattern that can be quite elaborate, 25 sub-pixel dithers if you want. But that was actually a little too tedious for me to put in PowerPoint, so I haven't shown that. But you can do that. You can choose a new filter and repeat the whole activity. And you might want to take a direct image to calibrate to flux calibrate the AMI image. You might want to do that, you might not. That's your first visit. Your second visit, you want to get a reference star, something that you think you know is a single source. And so you want to do this contemporaneously within 2 weeks so that the telescope, the figure of the telescope hasn't been changed. You want to repeat the sequence identically, and you're going to use those data from the reference star to derive closure phases and closure amplitudes. Those are terms that those of you who use ALMA or the VLA will be very familiar with. but for today, we're going to punt them down the road and talk about them in the next workshop on calibration. Here's some predicted performance. So this is as we go from bright things up to fainter things, and this is the magnitude difference between the bright thing and the faint thing that you're trying to find, the exoplanet that you want to characterize. So you see that for a G85, 6.5 magnitude star, you can have 9 magnitudes of contrast. That's the prediction at this separation, the inner working angle of 0.7 or 70 milliarc seconds, 0.07 degrees. So that's pretty cool. And that's something that the coronagraphs will not be able to do. Let me just say very quickly that also if you're looking to do synthesis imaging, so that is you take an image, do this whole AMI thing at one time, and then wait for the field to rotate by 90 degrees and do it again, you will have filled the UV plane, or at least more filled the UV plane, and you can actually derive an image. Here are some simulations of model structures around AGN. They're obviously very contrived. And then we put these simulations all through our machinery to fuzz out the data and then try to recover it. And you see that we recover things pretty well. And so you think, well, that looks like a pretty crappy thing. And I wouldn't disagree. On the other hand, though, the scale here is exactly 1 pixel. The width of the bar is 1 pixel. And you can't do that with normal imaging. Right, I think I'm out of time. So let me summarize. NIRISS has imaging capability with a filter set that's closely matched to NIRCam. This imaging capability is an integral part of AMI. It's an integral part of our wide field slitless spectroscopy. It's a powerful mode when used as a science parallel. But you should use NIRCam for all your imaging needs. We have aperture masking interferometry, which is also a powerful capability that provides very high spatial resolution and good contrast. It's very stable and it's self-calibrating. It can be used for synthesis imaging. So it seems tautologically true, but AMI is a friend, and so you should use it. It's an exciting time for all of us, and so let's vamos. Okay, thank you.